Now that we've made our layer of glass insulator on the silicon wafer with the thermal oxidation step, we're ready to learn another one. So we'll do this in one of the other clean rooms at Georgia Tech. This one's the Marcus Nanotechnology clean room. So remember that every circuit needs electrically conductive wires to guide the electricity to where we want it. So in this step, we're going to cover the wafer with a thin metal layer, and then in the next step, after this one, we'll use a special type of corrosive acid to eat away just the places where we don't want wires. So when we're done, there will be thousands of tiny wires arranged just the way we want them for our circuit. So the remarkable thing you'll see is that we don't have to make each wire individually one at a time. We make all 1,000 of them at the same time in parallel, basically. This is a really powerful idea and is what allows computers to get more and more powerful every year while still costing the same or less and less for a more powerful computer. So a real microchip like a Pentium, for example, has billions of tiny transistors and circuits on it. A billion is a million times more than we have on our small wafer, and it would actually take a really, really long time just to make one wafer of microchips if we had to make each circuit one at a time. So as you'll see, we can make all the circuits at once on the whole wafer, so it takes the same time to make 1,000 circuits as it does to make a billion. And so, since time is money, we can make more circuits in the same amount of time, which means we can make more powerful computers for less money, and everybody wins. So this is how your modern microchips are made. They make all the circuits and all the microchips on one wafer in parallel, and then chop it up into pieces, and then sell each of those individual microchips to go into your computer at home. So let's get on with it and head on into the clean room. So first I need to grab my wafers again and get them out of the storage area and then go log into the tool. The tool we're going to use today for coating the wafer with metal is called a sputterer. And a simple way to think of a sputterer is that it's kind of like a fancy sandblaster. So basically we're going to shoot a bunch of gas molecules at the surface of a pure piece of metal, and when the gas molecules hit the metal, then they'll knock off some of the metal atoms. The metal atoms are then going to float around, and some of them are going to land on our wafer, which will slowly coat the wafer layer by layer with thicker and thicker layers of metal atoms. So the way that we shoot the gas molecules isn't really like shooting them out of a gun. It's a little more complicated, so it may not be familiar to you. Basically, we're going to use electricity to charge the gas atoms inside of the tool. So the tool has this chamber, and inside of it we're going to fill it with a special type of gas and then zap it with electricity so that the gas atoms will become charged, and then they'll move back and forth when we apply a sine wave to it, basically. And as they move back and forth, they're going to hit into the solid metal piece that we have in there called a target. And when they hit the target, they're going to knock off, as I said, they're going to knock off metal atoms, which are then going to float around and land on our wafer. So a gas that behaves like this is called a plasma, and you'll see that it looks a lot like what you've already probably seen in your home or at school in a fluorescent light bulb. So it may look kind of familiar to you. So this round metal disc that you see me putting into the sputterer is called a target, and it's basically just a very, very pure chunk of metal that we're going to use to coat our wafer with. So in this case, the target we're going to use is 99% pure aluminum and 1% pure copper. As you can see, we have to wait a while after we put the target in and close the lid. This is so the sputterer can pump all the way down. So basically we need to pump all the air that filled into the chamber when we opened it. We need to pump all that air back out, and this can take a little while to do. So we have to pump all the air out so that we can fill that vacuum then with just the special type of gas that we want to use, which is argon in this case. And by controlling what type of gas we have in the chamber and the way that we pulse electricity into it, we can control how the plasma behaves, which means we can control how those metal atoms come off of the target and land on our wafer. So once the target's in place, the next step is to load our wafer into the tool with a load lock. A load lock is, as you can see, it's kind of like an airlock on a spaceship, and it basically just lets us take our wafer from atmosphere where we have all this air around us and put it quickly into the tool that we pumped all the air out of without letting any air into the chamber. So it saves time and cost. So now as we continue to wait for the chamber and the load lock to pump down all the way, we'll speed up the video because this can take quite a while. So once the pump down is complete and there's basically no air left in the chamber, we're ready to start prepping the tool to make a plasma. So we have to enter in a bunch of numbers and turn a bunch of knobs, which will tell the tool things like, what type of metal we're using and how many metal atoms per second we want to land on our wafer and how long we want this whole step to take. So these things affect the quality of the metal film that we're the metal layer, I guess, might be a better word, that we're depositing on the wafer. So we want to have control over all these parameters because that controls how nice the film is when we're done. So we have to be careful that we don't put in the wrong numbers so that we don't mess up the metal layer on our wafer, and also so that we don't damage the tool or damage our wafer. So now that everything's set up, you can see that there's a purplish kind of looking plasma glowing inside of the chamber where our wafer and where the target is. And now we just need to wait till the step is finished. So the plasma is going to bombard and basically shoot and push those gas atoms from the plasma against the metal target that's sitting in the chamber, and the metal atoms will slowly float off and coat our wafer. Once it's finished, we're ready to get our wafer back, and you can see now that it looks like a piece of aluminum. So we took a silicon wafer and we've coated a very, very thin, pure layer of aluminum plus a little bit of copper onto the surface of it. So now our wafer is ready for the next step, where we're going to use sort of a photographic film with a stencil, basically, and corrosive acid to eat away the metal wires away from the places where we don't want them. And so wherever we don't have acid touching the metal, basically we'll leave a wire behind, and that's what will form our circuit.